So we're very familiar with the basic formula for determining average speed in terms of linear speed. We know that we measure speed in miles per hour. It's usually measured in terms of some distance divided by some time. Now we want to start thinking about this in terms of angular speed. So that's our linear speed. Our linear speed is that distance divided by time. It's on top of the previous page. So when we talk about an average rotational speed, we need another symbol. I'm not going to use V again. Technically, I'm not using W. The symbol that we use for angular speed is omega. It's the Greek letter omega. You can see it printed here. It's similar to a W. Mine looks very W-ish right now, but it's a little more like curvy, I guess, than a W. So that's a better omega right there. Okay, so we talk about omega as being the average rotational speed by considering angles in time. So omega would be, instead of a distance measured in, say, miles, it would be a distance measured in some angle per some unit of time. Okay, now if I put that together with the formula that I've used for radian measure before over here, that the angle is the arc length divided by r. Okay, so angle is arc length s divided by r, and if I rewrite this, one second, to solve for s, that would be theta, times r, there we go, solving for s here, theta times r equals s. Now, theta times r equals s is a distance. That's an arc length, the distance. So if I combine that with my traditional speed, that would give me v equals, instead of distance, since arc length is a distance, I could put theta r up there divided by t. Now I have a theta divided by t, and that is omega. So we can get this relationship here between linear speed and angular speed. And that's what we have right here. It's just written in the opposite order, but same thing. So I've got the omega times r, angular speed times r is linear speed. Okay, so let's look at an example. A water wheel has a 4-meter radius and turns due to the flow of a river. After watching the wheel, you notice that it makes about 8 full revolutions in 1 minute. Estimate the linear speed of the river. Okay. One of the first things that we're going to have to do is convert revolutions per minute into angular speed, which is going to be measured in radians per minute. So I can convert that because I know how many radians are in a revolution. So 8 revolutions per minute is the same thing as 1 full revolution is 2 pi radians. So I can convert this by multiplying by the fraction 2 pi radians divided by 1 revolution, just using some unit conversion right here to cancel out revolution. And this is going to get me 16 pi per minute. I don't have a unit up there on top, but that is radians. So that's 16 pi. I can write rad for short, radians per minute. So what they gave me was not quite in terms of angular speed, but now I know what omega is. I know that omega is a measurement in radians per minute. All right, I want something there that's going to have angles on the top, right? Angles measured in radians. Okay, so now that I have the angular speed, I can estimate the linear speed of the river by multiplying it by the radius of that wheel. So my linear speed is going to be r, which is 4 meters times 16 pi. Remember, radians are technically unitless. I don't have to write them. I can just say it's 16 pi per minute, and that's how I come out with the units of meters per minute, because radians truly are unitless. The unit is not actually necessary in that piece. So back over to a calculator. I've got other stuff on there, but that's fine. I just want to figure out what 4 times 16 pi is as a decimal so that I have an approximation for my linear speed. Linear speed is about 201.06 meters per minute. So I took something that was angular speed in revolutions per minute, made it radians per minute, then I was able to convert it back into its linear speed component. Cool. So in part B, if the water wheel kept spinning at this rate, and it would with a constant water flow, how many days would it take for it to rotate 1 million times? All right, let's find out. If I want it to rotate 1 million times, that means that I want 1 million revolutions. I'm trying to write a million. Let's see. There we go. I need one more zero. 1 million revolutions. Here it's going to be most efficient to use the speed that was already in revolutions per minute, and then I just need to solve for how many minutes it's going to take to equal 1,000 revolutions. So if I had 8 revolutions for 1 minute, I want to find out how many minutes to get 1 million revolutions. So I can use a proportion to solve this. So if I multiply the x over, I can divide the 8 over. So 1,000, a million, I meant to say, divided by 8 comes out as one more zero, there we go, divided by 8 comes out as 125,000 minutes. And we could convert that time if we wanted to. Say convert it by 60 would give us hours, or convert it by 24 would give us days, so 86 days. Let's go 86.8 days. All right, so to answer our question, how many days? Oh, I forgot that even asked me about days. Good thing I converted to days. I had it in minutes, so minutes, of course, there are 60 minutes in an hour, so I divide by 60 to get it into hours, and then there are 24 hours in a day, so I divide by 24 to get it into days. 86.8 days for it to rotate 1 million times. All right, I think we have 1 page left. Okay, example, an SUV has tires with a 17-inch radius. If the SUV rolls forward 4 feet, what is the angle of rotation for the tires? Here we will be using the angle equals S over R formula. In this case, the arc length that we're talking about is going to be the 4 feet. As we roll our tire, we're going to be tracing that tire down. So that's going to be the end point, is going to be where we land on the tire as the tire rolls. So the arc length is going to be that horizontal distance, because we're going to be tracing around our tire up to a distance of 4 feet. The radius is 17 inches. Of course, the units aren't the same, so let's convert them both into inches. 4 feet is 48 inches. Divided by 17 inches. It gives us 48 divided by 17, just got a calculator right here, gives us an angle of 2.82. That is in radians. So 2.82 in radians would be the angle. To get a sense for what that means, I can convert that to degrees real fast. So, or if I multiply that by 180 divided by pi, that gives me an angle of 161.78 degrees. So just again, sometimes we're a little better at thinking about angles in terms of degrees. 2.8, I'm not sure how far around the circle that is, that having it in terms of pi. So 161 degrees, I know it's less than 180. To see if this makes sense, let's compute the circumference of this circle. The circumference of a 17-inch circle is going to be 2 times 17 times pi. So the circumference is 106 inches, and we've only gone 4 feet, which is 48 inches. So we have not gone around the whole circle. We've gone a little less than half, and 180 degrees, a little less than half. So that's our angle, if that makes sense. Okay. So our angle is a little less than halfway around the tire. So we're up here somewhere when we stop. All right. If the tire rotates 35 times, how much distance has the SUV traveled horizontally? Now we're going to fully rotate 35 times, and one full rotation is going to be all the way around the circumference. So 1 revolution equals the circumference of 2 times pi times 17, which we said was 106.81 approximately. And so that's one revolution. If the tires rotate 35 times, how much distance does it travel? So if I multiply this by 35, so our 34 pi times 35 gives us 3,738.5 inches, but we'll divide that by 12 to convert it into feet since the original distance was given in feet. So that gives us 311.54 feet. So if the tire rotates 35 times, it went 311.5 feet. All right, the last example. The Earth is roughly a sphere with a radius of about 4,000 miles, which rotates about once every 24 hours. What is the linear speed of a person standing on the equator due to this rotation? What about someone in Jackson, which is approximately 42 degrees north of the equator? The first thing that we can do here is define the omega, the angular speed, based on the fact that we're rotating about once every 24 hours. So they make 1 revolution per 24 hours on the equator, which is 1 revolution is a measurement of 2 pi per 24, or pi twelfths. Putting my units back on this is pi 12th radians per hour. I don't have to write radians, but I will write the per hour portion of it. Now that I have the angular speed, I can get the linear speed, because linear speed is radius times angular speed, and I know that the radius is about 4,000 miles. So the speed is 4,000 miles times pi twelfths per hour. Okay, just going to grab a calculator real quick. I think I have decimals open. Excellent. So I can divide, I've got 4,000 times pi divided by 12 gives us an approximate speed of 1,047 we'll just call it 0.2 miles per hour at the equator. Okay, so now we're going to check out how fast the person at Jackson is moving, not the person on the equator. So I'm going to try to draw in some angles right here. So if we're at the center of the Earth, this comes out to the here, of course. Let me try to draw it separately. So I'm at the center of the Earth. If I angle up to Jackson, we're going to turn the Earth so that Jackson happens to be right there. Okay, so instead of looking at it where Michigan's in the center, oh, sorry, guys, I forgot to switch my screen. Great. Okay, so we're going to turn the Earth so that we make sure that Jackson's right here on the corner. So when I arc my angle right here, that I can use a radius to get out there to Jackson, and then I can use a radius to get out here to the equator. Okay. And then I have this arc that is going to be 42 degrees in measure, because Jackson's approximately 42 degrees north of the equator. Okay, now both of these sides are R because we've arced from the center of the Earth out to Jackson and out to the equator. What I want to know is what Jackson's radius is on that sphere. So I want to know what this measure is, but that measure is the same as this measure. Okay, I've got my full arc, but that triangle would drop down to be just Jackson's measure, just a shorter radius, right? So that's what I want to find. I'm going to call it X right now, that radius for that shorter measure. Okay, and I can find that using, since I have the radius up here as the hypotenuse of this triangle, this is the adjacent, so I can find that using the cosine. So if I use the cosine of 42, that's going to be equal to our x over r, where x is our new radius for Jackson. That is 42 degrees. I'm going to put the degree measure up there. I can go ahead and plug in the 4,000 for r. So the cosine of 42 degrees equals x over 4,000. And if I'm in degrees, I can compute that cosine and multiply by 4,000. So we'll do that. Okay, I'll try to remember to switch my screen back here. Let's make sure I'm in degrees. Yes. And I can multiply the cosine of 42 degrees by 4,000. And so that gives me an x value of 29,000, 2,900, or 2,972.58. Okay, flipping my screen back. Don't forget to do that. And that's in miles. Okay, so this is the radius in Jackson. So if I try to calculate the velocity for a person in Jackson in terms of linear speed, the radius instead of 4,000 is going to be 2,972.58 miles. The angular speed is still the same. I still have that I'm doing 1 revolution in 24 hours, or a pi 12ths per hour in radian revolution. So if I change this to be that new speed, is going to be, the new speed is going to be 778.2 miles per hour in Jackson. So in terms of linear speed, we can see that a person who lives at the equator is moving in a linear speed much faster rotationally. They have further to rotate, so they have to move faster to keep up than a person moving in Jackson, where they live much further north of the equator. Again, if I just flip back, I was just pointing at stuff. So there we have it.